So do you see my screen? So pure aloha, probability that k frames are generated within the unit of time t is as follows. Oh, it's nothing different but what we talked about in Poisson distribution, okay? That we strictly follow this equation. So, k frames are generated in given time t is as this follow equation. So let's assume in a given time is 1, I'm generating k frames, meaning I am following this equation, meaning because my probability, so probability of success is I am the only one who talking, I'm generating the packet. Also, everyone else should not speak for 2t. Clear? So I am talking, everyone else is silent for 2t. So probability that no traffic is generated within 2t is as follows. So t is a 2, you put a 2 in here, 2, k is 0, then it will be 1, then k is 0, therefore it is 1. So e to the power 2g, e to the negative 2z is your probability that no traffic is generated within 2t, and I am the only one who talking. Okay, then arrival rate times the successful probability is this one. Clear? So we talked about the Poisson distribution and we know how to calculate it. And we are strictly following the Poisson distribution in this slide. And to make, we understand what is the aloha, we understand what is the medium access, then how do you make your medium access successful? Meaning you are talking, but everyone else is silent while you are talking. Meaning while you are vulnerable. Okay, so we have to calculate the probability that the no traffic generated in your vulnerable time, and I am the only one who talking. Then this is successful probability. Okay, so slotted aloha. From now until this point was continuous aloha. Okay, so continuous aloha has 2t vulnerable. Continuous aloha has a 2t vulnerable time. Okay, probably 2t generable time. Why? Because we have continuous time. So we're going to talk about what is the slotted time. So slotted aloha is the concept of divide the time into slot. Time is divided into slot. Huh? What is this? So back to So previously, my time was just continuous time. Now, my time is slotted time, meaning I make a slot. So communication only start at the start of the slot, or no, right? So you cannot start from here because time is slotted. So we make a time a discrete time, okay, not continuous time. So we call the slotted time, the slotted aloha. So collision would occur in a slot n if more than one arrival slice and n-1, meaning if I have something to digest, so I am sender, there is receiver. If something is coming, what do? You wait for the next slot. If the something is coming in you receive it, and when do you start? Previously, it started from here, which is not good, which is not a concept of the continuous time. But from here, if you receive this point, meaning you're waiting for your earliest available time, which means the next slot time, then you transmit in this position. Clear? This is what I mean. So a collision will occur in the slot n if more than one arrival occurs at n-1. Ah, okay. So no arrival meaning unused slot. So if there is no arrival at that packet, at that slot, meaning you may vacant in a following slot. Okay. So something like this. If the package is coming, message is coming in here, you talk in a given slot. In this given slot, there is nobody, then slot 2 is wasted and vacant and not used. And two slots, two packets are need to be delivered, then at the slot 3, there will be collision by the two transmitter because they will compete. Okay, then empty time for long, and there's some slot later, they will try to retransmit. Okay, so we're gonna talk about this. So now we understand the concept of a slotted aloha. Okay, what's the vulnerable time in a slotted aloha? Nobody? So we understand the vulnerable time in the continuous aloha. What's the vulnerable time in the slotted aloha? Anyone?
T.
Yeah. How?
Because in this aloha, they are divided at exactly T slices.
Okay, perfect. Who's this?
Janar.
Thank you. So everybody understand the vulnerable time? So let's go back to the point. My vulnerable time in continuous time was 2T. Oh, now we understand what is the 2T in the vulnerable time. Now, what if it is slotted? What's my vulnerable time in this slot? So my vulnerable time is only from here to here because every time is slotted. Okay, do you ever clear? Now my vulnerable time is T. So what's the successful rate, successful transmission? Meaning I am talking and nobody else is talking. Meaning I am the only one. There is only one talking. So K is 1, in a T is 1. K is 1, T is 1. Then therefore G e to the minus G. Okay, so probability of the idle slot, meaning nobody talking. In a given time T, in our case is 1, and nobody talking is a 0. Okay, time T in the 0. Then you're applying this numbers from to here, then you'll get this. Clear? So what's the probability collision? Collision meaning out of all possibility, I eliminate successful and eliminate the idle, meaning there is a collision. What's the wasted slot? Meaning out of all probability subtracted by my successful communication, successful transmission. Clear? So probability of the successful transmission, oh, I get this by applying this equation. Okay, probable idle slot, oh, I can get this by applying this equation. And what's the collision? Collision meaning 1 minus successful wasted. 1 minus successful idle is my collision. And wasted is 1 minus successful. So collision is also wasted, idle is also wasted. Clear? All right, so any other cases? So in the throughput of, in the slotted aloha, in the paper of the slotted aloha, this is the only case they covered. So pure and slotted aloha. When pure aloha, where vulnerable time is 2T, this is the throughput. Throughput per frame time increasing as attempts per packet time is increased, meaning attempts per packet time, meaning there is more and more packet. This means more messages. This is your performance. X-axis is more packet and Y-axis your performance. Okay. In a vulnerable time 2G pure aloha, you'll get this curve by applying the equation that we saw today. Okay. And if you have slotted aloha, oh, in this almost same environment, your performance is definitely increased at peak at 1 and previously at peak at 0.5. Why is the peak at 0.5 in 2t? 2t pure aloha? Because your borrowed time is 2t, therefore you have to talk, you have to be only 1 in a 2t. Therefore, 0.5 is a peak. In a slightly aloha, if you are the only one talk, then that will increase them. That will be the highest point for the throughput. Do you understand this this figure? Everyone clear about this figure? Want me to do it again? Okay, let's do it again. So we talked about the pure aloha and slightly aloha. What's the difference between pure aloha and slightly aloha? Pure aloha has continuous time. Slightly aloha, we make the time to slot. Then is it really successful? Is it really helpful for the better communication? Yes. So G, x-axis is G, attempts per packet time, meaning more packets and more messages on y-axis. And S is your performance, throughput per frame time, meaning your performance. So aloha, which has 2t vulnerable time, has this curve, throughput curve. Where's the peak? At 0.5. Why? Because you have 2t vulnerable time. Within the 2t vulnerable time, if you are the only one, then your communication will be successful. Therefore, in a given time slot 2, if I am only 1, I'll be successful. Meaning, therefore, 0.5 attempts. If the 0.5 attempts in a given time, then it is most efficient. Say I am using a slotted aloha. Slotted aloha meaning I am more advanced. I divide the continuous time into discrete time, meaning time is slotted. Therefore, if in a given slot time t, if I am the only one, I'll be successful. If not, my performance drops. So when I am the only one in a given time t, my performance at peak. Then if it is there more than 1, then my performance goes down, and smaller than this, less than this, and also the performance goes down. Clear about this figure? Okay, because silence is acknowledged, right? No? Where are you guys missing? Okay, clear, thank you. So, how about everyone else? Good?
Yeah, I think I got it.
Okay, all right, so, let's move on. Can I move on? Okay, so move on to the CSMA. CSMA is a carrier sense multiplexes, meaning carrier sense. Before I talk, I sense the carrier. I become more smarter, right? Previously, I just talk when I have messages. But from now, I sense the environment. Meaning, if I want to talk to someone, I'm waiting for my timing. When everyone else is not talking, then I can talk. Then carrier sense multiplexes. This is still used in most of Wi-Fi and most of the competitive-based communication. So stations listen before transmission. So before I talk, I listen. Okay. So there's many mechanisms in CSMA. Start with this one persistent. One persistent is station listen to the channel continuously. If the channel is busy, wait until it is free. If the channel is free, transmit. Right after, I have opportunity. So if the channel is busy, keep silent. If not, right at the time I start. Okay. So if the collision occurred, wait for random amount of time. Therefore, I may sigh for a while, then waiting for next chance. Then I start to sense it again. Do you understand? So one persistent.
Professor,
Yeah.
why does it say if the channel is free, then transmit with probability 1?
Okay, let's say, okay, with probability 0.5 and 0.1, 1.0. Let's say I have 0.5 probability 1. Meaning, if the channel is free, I am talking right now. That is 1. Meaning, if the channel is free, I am talking right now with the probability 0.5. Meaning, I am talking, maybe not. I'm talking, maybe not. That is 0.5, 0.5%, right? What is the better? What do you think? 1 is better or 0.5 is better? Let's think about, I have 30 guys in one classroom and everybody waiting, one guy started talking somehow, and after his talk is done, if we have one persistent, everyone else is talking at that moment, then a collision. With the half probability, with the 50% probability, everybody is, when the time is given, when there's available, with the 50%, they all will talk. If I have 100 people in a classroom, if I have 0.01%, meaning if the channel is available, only one guy will talk. Then, in the view of the communication, that is more efficient. Why? Because everybody.
Yeah, because we distribute the.
Yeah. So
and
more prompt to error. Right? Clear? Probability 1 means I am talking whenever there is available. Whenever there is available. 0.5 meaning 50%. If there is available, I may or may not with the 50%. 0.1 is I may or maybe not with the 10%. I may talk in 10%. But I may take the next chance. Why? Because I know there's many competitors in the town. I have to share the medium. Did I clarify your question? You can continue
yes.
asking. Okay. All right. So now we understand the concept of one persistent. There is more and non-persistent, meaning non-persistent. If the channel is busy, defer from sensing for a random time, then better medium utilization than a persistent PSA. Meaning, say I have time period, and someone is talking. Then, what's the P was doing? What's the 1 was doing? Oh, channel is available. I am talking. Then everybody else may be talking. Okay. Then with the probability, I may or may not on this P persistent. Non-persistent is doing in a given time. I sense something, meaning rather than I'm waiting for available time, I'm defer for a while, defer for random time, and check the channel again. If the channel is not busy there, I may start. So your receiver is less actively working. I don't need to sense. But I'm periodically sensing it, defer for random time, defer for random time. Okay. So if the channel is busy, defer for random time. If not, I can sense. Then after this, I'm defer for random time. So better medium. So this defer time P non-persistent is better utilization than persistent CSMA. Okay, we're gonna talk about. So P persistent is previously 1 non-persistent and P. P is a probability. If the channel sends the busy, transmit when idle with the probability P, else wait for time. Okay. Low throughput on low loads due to the idle time and improves the throughput on high load. What is this? So P persistent, I assume you understand the 1 persistent. P persistent is the probability that you are saying, with the 10% I'm talking, with the 20% I'm talking, with the 1% I'm talking right now. Non-persistent, rather than waiting for the time I sense, defer for a while, defer for a while, defer for a while. Okay, let's look at the performance. We understand the pure aloha. We understand the slotted aloha. We understand the 1 persistent CSMA. It's better than an aloha, 1 persistent CSMA. And 0.5, it works better when there's more traffic. and 0.5 and 0.1 is better when there is more traffic, and 0.01 is better when there's more traffic. Also, look at this, non-persistent. Before time works better somehow, right? So this is purely based on the theoretical background. So in reality, we adapt P-persistent CSMA in a Wi-Fi, in most of the walkie-talkie communication, and all these things. Okay. Are you clear about this graph? Do we
Professor,
now? Yeah.
can you explain what S really means? Like, why is it bounded by 1 and 0?
S? Where is that?
Yeah, the y-axis.
Oh, S is your performance. Higher the better. So throughput per packet time. That's your performance. Meaning I can deliver more communication. So X is more packets, more messages you need to deliver. Okay, attempts per packet is, oh, I have to deliver more packet. So there's more attempts, meaning there is a busy, your channels are busy because you have to deliver more. The more simple concept is x-axis is, oh, I have something to deliver. I have smaller things to deliver. I have more things to deliver on. And y-axis meaning, oh, I am successful. More successful, higher the better. I can be more, I can deliver more and more.
So 1 would mean that it's
This
like
one.
that's all the time?
This one means, right?
Yeah.
1 is a, so theoretical upper bound. You are 100% utilizing.
Oh, all right. So it's in percentage, right?
Yes.
Are you saying? Okay.
So 0.1 is you are only 10% using the throughput, the given theoretical upper bound. So you cannot exceed here.
I see. Thank you.
All right. So now we have a knowledge to understand this figure. Clear? Okay. Do you have better mechanism than this? How's the Wi-Fi in today's technology using this? No? Any concept? Any idea? So this is like early 2000 and until 2005, this kind of paper was coming to the market, and now it is mature. And how people mature, how people advanced. What's the market leader? Industry's choice. What is the, so let's think about for 1 minute. So what's the best way to do this? What's the best way to utilize your given channel? Let's think about for 1 minute and listen to your idea. Okay, ready?
Yep.
Yeah, go ahead. What's the idea? How do you utilize better?
I think it involves either buffering or multi-channeling. Like we use Wi-Fi like with multiple phones like at the same time, right? So it might just make multiple channels and allocate allocate the entire bandwidth to those channels, so that like multiple devices can send packets continuously.
Okay, so who's the speaking?
Janar.
Janar? Okay. So Janar says a multiple channel. That is great concept, and we are using that, yes. But in Wi-Fi have 13 channel. And among 13 channel, we are using 11 channel. And when we are fixed to the one channel, let's say channel 1 to 11, when your communication, your AP is choose to communication 2, that channel is fixed. AP does not hop. When there is a channel 2 is open for the AT, that is assigned, meaning you cannot change unless you are resetting or rebooted or like any software setup. So let's simplify the scenario. It's a good point. Thank you, Janar. Anyone else? How can you overcome this? We are not achieving 100%. And how's the market's decision? What's the market decision? Any idea?
Can we send packets in like different frequencies?
Sending a different frequency, then allocate like a schedule.
Allocate like I don't know. FCC does this like what is it? Coordination of frequencies, right?
Coordination of frequency. Okay, so David talked about FCC. So FCC is a frequency commissioners like a committee, something like this. Okay, that's the Federal Communication Committee, and they make decision who's allowed to communicate, who's not allowed to communicate. Okay, so that is from the very lowest band to the highest band, some terahertz. So this frequency is for LTE, this frequency for the military, something like this. It is all allocated. But in the communication, in the basic communication, you are using this very small channel. So FCC is a regulation, a high authority. Your communication needs to be played in this. If you are violating, and your communication will not be continued, and you will be punished by the law, something like that. Okay. Therefore, it is above the concept. So we talked about, okay, in a given Wi-Fi communication, how can we improve the utilization? That's the question. So we talked about, we use the CSMA, we use the one persistent. What's the better way? Do you have a better idea on this? Something like this. So maybe David said, okay, in a given frequency, I may have one competition channel, then the communication is still going on in like this, like a fast lane. Fast lane, they are communicating, and fast lane's decisions are controlled by this control the frequency. Is that what you're saying?
Yeah, I guess you're right. Yeah.
Okay. Thank you. Thank you.
Right.
Anyone else? So I'd like to hear your voice because we are online, and I don't want to make your cam is on for every time. So your participation make this class better, much better. Let's do some feedback. Any comment? No? So industry choice of the 2020, what you call OFDM. OFDM is a winner of the communication mechanism. What's the OFDM? Orthogonal T frequency division multiplexing. Multiplexes. Modulation, OFDM. Orthogonal frequency division. M is multiplication? No. Modulation? I think it is modulation. multiplexing. Okay. So orthogonal frequency division multiplexing. What is OFDM? How could it win? Eat up all the competitors, and OFDM is the king now, at least for 10 years. Most of the advanced, like your Wi-Fi is OFDM, your LTE is OFDM. And in the 5G, in a 6G, there will be all OFDM. How OFDM win? Okay, basically we are communicating in a given bandwidth. Let's say the LTE has a 20 megahertz. So if I'm sharing a news video, let's get up by SKP. So this is the news that there is a new frequency 3.5. And what it's saying is SKT KT for the 5G frequency 3.5 gigahertz is auctioned. Meaning this is SKT, KT, and LGU plus, and these are all related to 3.5. And for the detailed communication, 28 megahertz, 26 megahertz, 27 megahertz. Oh, no, that's the gigahertz. Let's look at the 3.5. 3.5, that's a giga, so therefore it's 0.200 megahertz. They have 100 megahertz. They are 80 megahertz, right? So how much is it? It's near like 1 billion. Near like $1 billion. So in Korean, 1조 2천억 원, 9천억 원, 8천억 원, something like that, near the $1 billion. That's the price of the frequency. Okay, so let's say you have a 80 megahertz, 100 megahertz. You have to pay almost $1 billion for this. Okay, so you are dealing with the very expensive environment. So how do you say, let's say you're a boss, just give you the 80 megahertz, and your job is utilizing and then better. So you have to use OFDM. Let's say you are given 20 megahertz. Oh, I have 20 megahertz. How can I use this? Can I use a CSMA? And everybody accessing a 20 megahertz CSMA? Okay, it turns out 1 persistent, P persistent, or D persistent, or 0 persistent, non-persistent, whatever it is. In a given 20 megahertz, what is the best way to utilize this? Okay, you have to use OFDM. What's the OFDM does? Let's say you have a 20 megahertz. First, you divide to the sub-channel. You divide to communication channel. It usually 2 to 10 megahertz. So in a given 20 megahertz, we may have 13 to 15 channels. In one channel, in a given one channel, you are using orthogonality of the frequency. So if I am dividing in here, I have to be silent in here, then I can start communication, right? That's the basic concept. But you know what? By using orthogonality of the frequency, I can so if someone is talking this way, I have to be using like this, right? Because I cannot overlap the frequency. But by using the orthogonality of the frequency, I can make this happen. I can make this happen. I can make this happen, and I can make this happen. This concept is called sub-channeling. By this sub-channeling, in a given yeah.
Can you explain the orthogonality of frequencies?
Okay, so
Does that
say I am using this frequency. My information is given in this guy and this guy and this guy in quadrilateral channel, right? But what if I am overlapping in this, meaning your communication is contaminated, right? But your frequency division is orthogonal, meaning 90-degree different. If there is one guy and zero guy, X guy, 90-degree different, oh, you are completely changing the axis to 90-degree, then I can distinguish, your receiver can distinguish between two communications because I'm receiving pattern as 90 pattern differences. Therefore, if you position 90-degree and you are using orthogonal, orthogonality is orthogonal to this, right? Using the orthogonality of the communication, then you are able to coexist. That is why the OFDM is an industry leader and market leader. So let me show you the some. So rather than a wide band frequency, I can have more and more by using orthogonality. So if I use, so the blue frequency pattern is not overlapping with the orange, not overlapping with the orange and the yellow and the purple and the green. So this maybe exceed the computer network class, but I'm trying to give you the concept of what is a leader on the industry. What do we choose? What's the today's technology? That is OFDM. So you may choose the OFDMA and OFDM in the YouTube slide. There is many YouTube slides and YouTube lectures. The basic concept of this is that if you can transmit two frequencies at the same time by using the orthogonality of the two channels. Two channels are not overlapping each other because you design the center frequency precisely that are 90-degree differences. That is orthogonal. Okay, in detail it's more complex, but the basic concept is that. Okay, all right, any question about this?
I have a question.
Yep.
So regarding the orthogonality, how many, so is there a limit of subcarriers for the?
There's no limit, but Wi-Fi using a 50 in a one channel, 50, LTE using more.
Oh, I see. Thank you.
Okay. All right, so how to detect the sub channels? There is a CSI, they call the CSI carrier sense index. If I go deeper, CSI. So there is the concept of the CSI. CSI is a channel state information. Channel information. That exactly give you the sub-channel information in the Wi-Fi. So I have a CSI chips. If you want to dig into more, I have some extra chips for CSI, 2 of those. So I used the, I wrote the paper on this by using the CSI. So if you want to dive in more, so I have experience on it. And if you curiosity wants to know this, and you can use my device. Okay, so let's finish the class with the last slide. And so CSMA with the collision detection. So previously we talked about the collision avoidance. How can you avoid the collision? Now, how can you detect the collision? Okay. So detect the collision early and abortion transmission, meaning rather than just avoiding it, if I know there is detect collision, then if I have ability to detect it, then I don't need to continue. I can quickly stop and I can wait for next time. So 2 types of slots. I make 2 types of slot, packet slot and contention slot. So each node try to transmit at a contention slot with the probability P. So if the collision, it is detected as atom the contention slot. If succeed, no transmission tried till the end of packet. Meaning, so let's say this is T0. This is T0. There is something, and I do have a contention period. Meaning, rather than I send a full packet, I make it very tiny, because even I lost it, there's a small damage to me, right? If I lost the full packet, my damage is also big. But if I lose a smaller packet, my loss is small. My damage is small. So in the contention period, everybody contention in a given time. The winner will send the full frame. Okay, so I make a time into two. One is contention and the other is transmission period. In a contention period, everybody contending. Then if you are the winner, then you can transmit at the transmit period. Contention and transmission. And if there is no contention, meaning there is idle, then you can start to talk. Okay, so if I explain one more time. So in a T0, the CD concept meaning if there is a collision, I can give up quickly. Therefore, I make a two slot. One is your actual packet. The other is your contention slot. Actual packet and small slot, which is contention. So I make it 2 times. In a contention slot, I'm sending small packet, which is purpose for. So can I send it? And pick me, then raise your hand. Then, you may talk. If I am selected, and I can send in a transmission period. Okay, so then I can give up quickly. If the my raising hand is not picked, I don't need to speak. Then I can save. I don't need to waste my energy. Okay, that is the CSMA-CD concept, collision detection concept. I divide the time period into the transmission and contention. Then it is more efficient. There's a more and more mechanism on this. How do you overcome this, and how can you improve the performance of the network? Then we're going to continue on Wednesday class. Any question about today's class?
Professor, is there a rule that, like, does the sender choose the contention slots? Like, is there a rule that, like, there's an algorithm that picks which of the contention slots that has to send the frame?
Randomly. If it is not random, if it is not random, it is not fair to everybody.
Okay.
So when we talk about the carrier sense multiple access, it has to be fair to everybody. If it is biased to someone, then your attacker will use this. So the greedy users will use this. So it has to be fair.
Like,
yeah.
Is this something like token ring in Ethernet?
Token ring. It is, yeah, some kind of concept. Yes, I can say that. Yeah. Okay. But it's more like advanced one. The basic concept maybe comes from token ring. Yes. So if I explain about the token link means if I have to share the medium with the 10 of people, I make one token. So I draw a token. Anyone else who grab it may speak. This concept that we call the token link. So maybe we hand it over one by one. Whoever holds the token may speak, right? But in reality, handing talking and drawing token is not possible. So we have contention period. If whoever wins this, then they can start. Okay, and conceptual-wise, it's very close. Thank you, David. Anyone else?
Oh, Professor, one more quick thing.
Yep.
In the last slides with all the graphs with the CSMA persistence, why was 0.01 persistent higher than non-persistent and 0.1 persistent, and how are they really defined in that way with the performance?
So this is the thank you, Tim. So this is result of the theoretical background. So I have a code for this, and I think I can share the code with you. pen, my pen. So let's say we understand about the pure aloha and slatted aloha and one persistent. Okay, now up to here I can understand. 0.5, oh, I understand. 0.1, oh, really, 0.1 better? And it stays better when there's more traffic. And stays better when there's less traffic. 0.01 meaning, let's say there is 10 people talking, 10 people talking. Then I may or may not talking with the 1%. Right? So if there is a 1, they can talk, which means your collision is more frequent than the vacant. When you are talking, then is collision. When you are not talking, that is idle. So what it's saying is, so if the vacant is more frequent, then so collision or vacant. So in this case, as collision is more frequent, then in here is a vacant is more frequent. In here is vacant is more frequent. Okay. So and somehow by the theoretical this amount. So in actual and reality, it is not true because it only counted these 4 cases: successful, idle, collision, and wasted. 4 cases. Okay. So based on this 4 possible cases, we added the concept. We try to say, oh, if we have a smaller and smaller probability, then you will have the better communication, because if you are talking, then your successful communication, the probability of your successful communication will increase because you will be the only one. If there is 2 or 3 people with a higher probability, then there is more people try to say, then you will be wasted and you have to defer time. If there is idle, the next time they will be talking, they will start to talk, right? So the concept of this one is what is more important? Collision is more critical or idle is more critical? This figure says, okay, collision is more critical. So if I am not talking, rather than I'm just keep silent for a long time, meaning I'm giving a better opportunity. This is what this figure says. And non-persistent is defer random time, defer random time, defer random time. It gives you a better environment. So these all graphs comes from a theoretical background. So in reality, it is not true. But so I can share this code. I will share the code after the class, and how I draw those figures, and you may play with this. You may see the more concept of it. Tim, did I satisfy the question?
Yeah, thank you so much.
Maybe I can explain more the face-to-face. Okay.
Thank you.
All right. So if after seeing the code, you will understand better. I will upload the code. All right. Anything else? All right. Thanks for coming today, and sorry for the late class. And have a good day today. All right. So I will upload your midterm score, and I will open the makeup exam schedule. All right. Thank you.